All right, so we've looked at an introduction to derivatives of exponential functions, and we saw that with the derivative of e to the x, we're pretty happy, right? So when we take the derivative of exponential functions with base e, we simply get that function right back. But watch out if it's the derivative of e to some function, so like a composition of functions, we derive the outside, which is the exponential, times the derivative of the inside. Okay, so this is the chain rule. He's always there. You can't forget him. And that's the way most people do make mistakes on these. So let's just do a quick one with this before we move to bases other than e. Okay, so for example 1, we're going to find the derivative of e to the x plus x squared. Okay, so again, it is its own derivative. So we leave it because the derivative of the outside function e to the x is just e to the x. Then we multiply by the derivative of the inside function. And when you do it here, it's super important we use parentheses because it's got multiple terms. So the derivative of x is 1, the derivative of x squared is simply 2x. Now there's not that much we can do here, like distributing it will just make it look even worse. The only thing we typically do is bring any coefficients, so to speak, out front. Other than that, not much else to see here. Okay, so just watch out for the chain rule. That's the moral of this story. Now where things get interesting is when we looked at derivatives of b to the x. Okay, sorry, that looks like I can't spell derivative. That's an R and an I. So we specifically looked at 2 to the x. And what we noticed is that the derivative of 2 to the x, unfortunately, was not 2 to the x. And this makes us sad because, man, wouldn't that be nice? It looked like it had been multiplied by some sort of scalar, some sort of factor. So we're going to use what we know about logs, and I know we remember this from pre-calculus, of course. We're going to use this property that says that e to the ln x is simply x. Or in other words, if we raise e to the natural log of something, it's going to give us that something, because exponential and logarithmic functions are inverses, which should feel very familiar because we've been talking about inverse functions. So they undo one another. And so it just leaves us with whatever we were taking the log of in the exponent. In this case, I'm going to pick this carefully. Basically, I want to rewrite 2 to the x as something with a base e, since I do understand derivatives with bases of e. And even though e and 2 are not far apart, they're kind of behaving differently here. So I'm going to get it to something I know how to work with. And so I'm going to set it up like this, where I'm going to substitute this as to what we're actually taking the derivative of. Now, I haven't actually taken the derivative yet. This is all just playing games to get it to a form we're more comfortable with. All right. Now I'm going to use another log property, which says the power of something I'm taking the log of is the same as multiplying it by that value. So that's really the same as finding e to the x times ln 2. Okay. And so now let's try this. I think this is doable. So if I take the derivative of this, I'm going to get that same function back times the derivative of this inside function. Well, I have x times ln 2. ln 2 is just a number, right? Like if I type that in the calculator, it's just going to give me a somewhat nasty looking decimal. So this is a constant. It's not pretty, but it is a constant. So when I derive x times some constant, I'm left with that constant. And this is where things get fun. Because now that I have actually found a derivative, I can make it look pretty again. What do I mean by that? Well, we originally came up with this form from this. So that means down here, this is really the derivative of 2 to the x, which is equal to 2 to the x times ln of 2. Isn't that awesome? So even though it isn't this easy, that's still pretty sweet, right? So the derivative of an exponential of any base b, let's write the actual rule here. The derivative of any exponential with base b is going to be itself times the natural log of b. And this works for any of them. So does it work for exponentials? Why do we have a different rule for e? E is just another constant, right? Well, let's try that. If we use this particular setup with our original e to the x, well, that's going to be itself times ln e. So how are we getting a different answer here than what we were just talking about? Well, our pre-calculus understanding of natural logs and exponential functions tells us that ln e, that's actually asking you e raised to what power equals itself, and that's going to be 1. So it is, in fact, the same exact thing we had already seen. It's just that this one's much easier to notice right off the bat, so you often start with that one. But really, we are always doing this general rule here for any base b. And similar to above, the derivative with a chain rule is still something to watch out for. Okay, so let's do a couple quick examples. So now that we know this, you know I'm going to be kind of mean to you, right? Not really mean, just sort of mean. All right. Our first problem is going to ask you to find the derivative of e to the x minus x to the e plus e to the 7, oh yeah, minus pi to the x. This is really fun. Okay, so the derivative of e to the x is just itself. We love those. Those make us happy. What's going on here, right? So be careful. I put these next to each other obviously because of the fact that people get them confused. Here the x is in the exponent, so it's an exponential function, so we use that derivative form. Here the x is the base. We've been doing these. This was actually the first thing you learned about derivatives, and this involves the power rule. So what do we do with the power rule? Well, the power comes out front and multiplies it, and we subtract 1. And Miss Wright was supposed to write that in red. Perfect. So that hasn't changed. E is just a number. Remember that. It is a constant. Speaking of e to the 7, well, what is that? Where's the variable there? I do not see an x with which to derive with respect to. So this is a way that they might be tricky. I don't see too many of these in A-B calculus, but it's not bad for you to go ahead and get used to this. E to the 7 is just a number. So when we derive a constant, it's just 0. And then again, here the x is in the exponential, so this is an exponential function. So it's going to be its own derivative times the natural log of that base. And here we have our beautiful answer. All right, for our second one, we're going to look at x to the 8 times 9 to the x. So again, I'm playing off of making sure we recognize polynomials versus exponentials. And let's just have some fun with the product rule in the meantime. So first, times derivative of last. So this will be its own derivative times natural log of its base, plus last times derivative of first, which is just a polynomial with a power. So 8 comes down, and we subtract a power. That's it. I'm not going to spend time making this look pretty right now. Moving on to number 3. So the derivative of 5 to the 3x. Now this one actually has 2 approaches, right? So let's stick with the basics here and just assume we've got a base of 5. So it's exponential, so it is its own derivative times the natural log of the base. So this step I just did is simply the derivative of its outside function, which we're considering 5 to the x. Then we have to take the derivative of its inside function, which is 3 to the x. So that would simply be times 3. Now guess what a lot of students want to do here that makes Miss Wright shed a very tiny tear. I often have students multiply 3 times 5. No, please don't. You cannot multiply the base of an exponent by just a regular scalar. It doesn't work that way. So how can I make this look any nicer? Well, you can simply write 3 ln 5 as the coefficient and then 5 to the 3x. That's about as much as you can clean it up. You absolutely cannot multiply anything times that base of the exponent. Now, what's the second way people might do this? Well, they might try to simplify it before actually taking the derivative. So really, we can think of this as 5 cubed being raised to the x, right? I mean, that's the same thing. And then we could go ahead and simplify, well, 5 cubed, that's just 125. Why might we do this? Because I no longer have to care about the chain rule, right? So that's simply going to be its own derivative times natural log of that base. Now, is this not a different answer than what we just got? Well, take a closer look, right? This part I can rewrite using my log rules as ln of 5 cubed, which, yes, is ln of 125. Okay, we got that part. And then we can do the same thing here where we kind of break this little section apart and then write it as this, which is 125 to the x. So in reality, either of them is fine with me, and you'll see both types of things happening on different AP questions. So you need to be very comfortable with your log and exponential property rules.